Hello everyone, my name is Pavel Valov. I'm a PhD student in University of Waterloo, and today I'm going to present our work called Transferring Pareto Frontiers Across Heterogeneous Hardware Environments. I want to begin with the introduction of minimal necessary terminology. Nowadays, modern software systems usually provide various configuration options. User-relevant configuration options are called features. Features influence functional properties, such as algorithms being used, system behavior, etc., as well as non-functional system properties, such as memory consumption and runtime performance. Unique feature selection defines a particular system configuration, and each configuration has a corresponding set of property values. For example, memory consumption and runtime performance. Actual property values vary across different configurations, and actual property values of configurations vary across different hardware environments. Here is a randomly sampled set of measured configurations represented by a table. Each row of this table represents a particular system configuration. Columns on the left represent individual system features. Columns on the right represent actual system properties for each configuration measured on different hardware environments. Now we can define a notion of Pareto optimality. Configuration is Pareto optimal if no other configuration can improve any system property, for example, system performance, without degrading some other system property, for example, memory consumption. In other words, each Pareto optimal configuration is optimal in its own specific way, and each Pareto optimal configuration provides trade-offs between different system properties of interest. After introducing the notion of Pareto optimality, we can define a Pareto frontier itself. We selected a configurable software system, bzip2, which is a general-purpose file compression system. We benchmarked the whole configuration space of bzip2 on Microsoft Azure Cloud Server. We measured two properties: compression time of the benchmark and resulting compressed size of the benchmark. We want time and size to be as small as possible. In other words, we want to achieve the best possible compression results within minimal amount of time. However, no configuration simultaneously provides that. Nevertheless, we have several Pareto optimal configurations that provide trade-offs between selected properties. Totality of Pareto optimal configurations define Pareto frontier of the system. Notice that Pareto frontiers can be different for heterogeneous hardware platforms, as we can see from benchmarking results of bzip2 system across different Microsoft Azure servers. We see that Pareto optimal configurations are different in numbers and actual system properties values. Needless to say that Pareto frontiers for different software systems have completely different structure even when analyzed for the same system properties across the same hardware environments. Imagine that a user has an access to a heterogeneous hardware cluster, for example, Microsoft Azure servers. User has to deploy and tune a configurable software system on top of this cluster. User starts by analyzing the system on one hardware and building a respective Pareto frontier. We've seen before that Pareto frontiers can be different for different hardware. So the main question is it possible for the practitioner to reuse this gained knowledge of Pareto frontier? Is it possible to transfer a Pareto frontier across heterogeneous hardware environments? However, building exact Pareto frontiers is challenging. First of all, we have a problem of limited information. Configuration space usually grows exponentially with the introduction of new features. while benchmarking itself might have a very limited budget. Analysis of individual configurations can be time-consuming as well. Secondly, we have a problem of heterogeneous hardware. Benchmarking results are usually irrelevant across differing hardware, and additional cross-platform benchmarking might be required. We can address the first problem of limited information by approximating property values of unmeasured configurations. On the left, you can see a sample of configurations with unknown values for a selected property. On the bottom, you can see a sample of configurations with measured values for the same property. We build a property prediction model, for example a regression tree, based on this sample of measured configurations. Then, we use this property predictor to approximate the property values for unmeasured configurations. Thus, we address the problem of limited information. We have discussed a way of approximating a single system property. But Pareto frontiers are built by analyzing multiple system properties. For example, bzip2 system has compression time and compressed file size properties. So how can we work around that? We can build a separate property prediction model for each started system property. And then we can approximate a Pareto frontier by individually predicting properties and by combining them into an approximated Pareto frontier. So how will the approximation process look in practice? Imagine that a user deployed a configurable software system across a heterogeneous hardware cluster. Then he trains an individual predictor on each hardware environment for each analyzed system property. Finally, a user can combine approximated Pareto frontiers based on predictions of property models. This way, a user can approximate frontiers separately on different hardware environments. However, that requires a lot of excessive measurements across different hardware. We can address the problem of heterogeneous hardware by training a property transferring model for each analyzed property and each pair of hardware platforms, and by transferring property predictors across hardware using trained property transferers. This way, we can save a lot of benchmarking effort by measuring only minimal amount of configurations necessary for building property transferers across cluster. So how do we train property transferring models? On the left, you can see a sample of configurations with unknown property values on destination server. On the bottom, you see a sample of configurations with measured property on both source and destination servers. We build a property transferring model, for example a linear model, based on this sample of measured configurations. Thus, by using this transfer model, we can capture a relationship between source and destination platforms. Next, we can feed configurations measured on source platform to transfer, and it will provide the property values on destination platform. Thus, we address the problem of heterogeneous hardware environments. So, how will the transferring process look in practice? Imagine that a user deployed a configurable software system across a heterogeneous hardware cluster. User trains an individual predictor for each analyzed system property and builds an approximated Pareto frontier on source hardware platform. Next, user trains an individual transfer for each analyzed system property and each pair of source and destination platforms. Thus, a user can transfer property prediction results across hardware and build a transferred Pareto frontier for each platform. The main goal of our research is to develop a pragmatic methodology that could be applied in real-world scenarios. This goal resulted in requirements that guided a development of our approach along with challenges mentioned previously. We assume that a user has no control over sampling process of a configuration space and might be restricted to historically benchmarked data only. Thus, in our experiments, we always use pseudo-random sampling in order to imitate this worst-case scenario of impossibility to make any sampling choices by a user. Moreover, we assume a limited information about actual system properties values that might not cover a configuration space entirely. Therefore, we analyze different sampling sizes in order to provide an assessment of how accurate predictors and transferers might be. Thirdly, we assume that a user works with a closed-sourced software system and might not have any understanding about internal workings of a system and won't be able to use this knowledge to improve predictors or transferers. Therefore, our methodology regards analyzed software as black boxes that output particular properties values given a configuration and a workload. Finally, users should be able to train predictors and transferers using minimal amount of training data, build and validate these models in a completely automatic fashion, and visualize the models in an intuitive way to get additional insights from training data and to verify that the models really work. We evaluated our approach using 34 different Microsoft Azure virtual servers. These servers have different CPU model, different number of CPU cores available, different total allocated random access memory size, and respectively different random access memory size per core, and finally, different storage type and size. CPUs used by Azure servers also exhibit strong variability. CPUs have different manufacturers, different architecture including technology node, core frequency, number of cores and threads, different instruction and data caches, and different benchmarking values for overall CPU performance and single CPU thread performance. We evaluated our approach using 5 different configurable software systems from data compression and multimedia transformation domains. Studied systems have different number of features and valid configurations. First of all, we want to evaluate how accurate are property prediction models. Here we present mean absolute percentage error distributions when predicting compression time property using regression trees as predictors. Each subplot contains error distributions of a particular software system. Each line represents an error distribution for a particular hardware platform. We can observe a strong decreasing trend in error with increase of a random sample size for all predictors. Moreover, majority of predictors achieve errors smaller than 5%, regardless of software and hardware systems used. Secondly, we want to evaluate how accurate are property transferring models. Here, we present error distributions when building transferers for compression time property using linear models. For all software systems, we observe a quick improvement in model quality with initial increase of a sampling size, with subsequent stabilization of error. This happens because a linear model quickly stabilizes and additional sampling does not change the overall fitting quality. Although linear models provide good results for bzip2 and gzip, other software systems exhibit worse and less stable results. Therefore, we decided to improve on linear models. So instead of linear models, we used regression trees as property transfers. Here again, we can observe a strong decreasing trend in error with increase of a random sample size for all predictors. Moreover, we also observe much more stable performance for different hardware environments. So far, we have discussed quality of individual prediction and transferring models. But how to assess quality of a Pareto frontier in general? We can regard a Pareto frontier as a binary classifier that separates all configurations into optimal and non-optimal ones. Thus, we can apply classical statistical measures for binary classifiers to assess a frontier. Here, we focus on 5 different measures. True positive rate is a probability that a frontier could catch all truly optimal configurations. True negative rate is a probability that a frontier left out all truly non-optimal configurations. These 2 measures assess quality of a Pareto frontier in general. Positive predictive value is a probability that a configuration classified as optimal by a frontier is truly optimal. Negative predictive value is a probability that a configuration classified as non-optimal by a frontier is truly non-optimal. These 2 measures assess quality of individual predictions by a Pareto frontier. Aforementioned measures are best regarded in groups, so we decided to include an integral measure of Pareto frontier quality. Matthew's correlation coefficient is considered to be one of the best measures for working with data that has strong quantitative differences between classes of observations, which is our case. First of all, we want to evaluate how accurate are approximated Pareto frontiers. Here, we present distributions of classification measures described previously. Each line represents distribution of a particular classification measure. We can observe a strong increasing trend with increase of a random sample size for each classification measure, and, respectively, for the overall quality of a Pareto frontier. We can also see that for FLAC, X264 and XZ software systems, true negative rate and negative predictive value measures, marked by red and orange respectively, have very high values even for small sampling sizes. This happens because the total amount of Pareto optimal configurations is much smaller than non-optimal ones. And even a frontier that rejects all configurations will get a high value of these measures. Thus, Matthew's correlation coefficient, marked by violet, provides a good integral assessment of a Pareto frontier quality. And we can see that Matthew's correlation coefficient increases linearly with increase of a random sample size. Secondly, we want to evaluate how accurate are transferred Pareto frontiers. These figures present evaluation results of linear-based and tree-based transferred frontiers for all software systems. Presented Pareto frontiers were transferred from the slowest to the fastest available server and thus present the most difficult scenario for evaluation of our methodology. Although linear regression demonstrated strong results for transferring prediction models of some software systems, figures clearly show that regression trees completely outperform linear models for majority of software. This difference is especially strong for FLAC and XZ software systems. Thirdly, we want to evaluate how much error does the transferring process add. To visually represent the added distortion to the approximated frontier, we calculated difference between approximated and transferred frontiers for all statistical measures. Thus, we can observe that the transferring process has a very limited impact on distortion of an approximated frontier, even for small training sample sizes. Therefore, we have demonstrated that transferring of approximated Pareto frontiers across heterogeneous hardware environments using regression trees is possible and doesn't significantly affect the resulting frontier's accuracy. We proposed and evaluated a practical, minimalistic, incremental, and black box approach based on general-purpose machine learning models for approximation and transferring of Pareto frontiers of optimal configurations. We thoroughly evaluated predictors and transferers for different training sample sizes, and we demonstrated superiority of tree-based transferers over linear-based transferers. We thoroughly evaluated approximated and transferred Pareto frontiers and demonstrated linearly increasing accuracy of frontiers with increase of a training sample size. Moreover, we showed that an overall accuracy of a transferred frontier depends more on the approximated frontier's accuracy than on the transferring process itself. Therefore, in future work, we plan to specifically focus on improving approximation of Pareto frontiers.